So speaker can start the talk.
Okay, can you hear me? Is everything all right? No?
Let's wait. I see you.
But can you hear me?
Okay, 1 second.
Yes.
Okay.
Yes, I can hear you.
Well, that's great. So we shall begin, I believe. Hello, we would like to present you our work that focuses on the development of an integrated approach to detecting emotions expressed in short, informal texts. Our presentation will be structured as follows. Sasha, please switch slides. Will you? Yeah, like this. Okay. So let's go.
Okay, so as it was said before, our paper focuses on the development of an integrated approach to detecting emotions expressed in short informal texts, combining linguistic analysis and machine learning. We propose an automatic classifier of text messages based on which emotions are explicitly or implicitly present in the text.
And some of the real-world application may include partial automation of linguistics text analysis and psychological testing in such fields as medicine, forensics, and HR management. Moreover, it may provide new capabilities in marketing and especially in targeting. Finally, it may also greatly assist in the creation of chatbots, dialogue systems, and further advancement of suicide prevention mechanisms on social media platforms such as Facebook.
Speaking of related work, as of now, researchers have achieved good results on image-based recognition. However, classifying textual dialogues based on emotions is a relatively new research area. Another challenge for automated emotion detection is that emotions are complex concepts with fuzzy boundaries and with individual variations in expression and perception. While a lot of progress has been made in this field, research into emotion detection in Russian language texts is still extremely limited. The present work is aimed at addressing this problem for Russian, and some features that we use are language specific.
Next, to develop an automatic classifier of emotions expressed in text messages, it is necessary to adopt a classification of emotions. As of now, there is no generally accepted one. However, Ekman's classification appears to be the most widely used. It includes happiness, surprise, sadness, anger, fear, disgust, and contempt. But at the current stage of work, we removed categories of disgust and contempt for the lack of appropriate data. Moreover, the categories of fear and surprise were merged into the one category of uncertainty due to certain similarity of the ways in which these emotions are usually expressed. Thus, the classifier presented in this paper recognizes 5 categories of text, according to the emotion most vividly expressed in it. It is happiness, sadness, aggression, uncertainty, and neutrality.
Okay, let's talk about data. Our work is focused on the informal inference-based discourse of personal messaging. For the purposes of our research, we compiled new corpus of text messages. The compilation process included 4 stages. Firstly, sourcing and parsing of data. Secondly, data preprocessing. Thirdly, data processing. And finally, corpus annotation. We also want to mention that to create our message corpus, we chose personal messages and public messages and public chats from Vkontakte. It's a social network often used as a messenger, and Telegram, a messenger with some social network features, to create our message corpus. It's legal as stated in GDPR, or General Data Protection Regulation. We chose these services because they're highly popular among Russian-speaking people. So the final collection of lemmatized messages consisted of 1,08,800,000 messages, which on average were 4 to 5 words long. The statistical population of an average Russian speaker was represented by the sample of almost 4,500 of people.
And it was one of the bigger challenges to annotate the messages with emotion labels correctly and objectively. And to do so, it was decided to use emoji ideograms as an objective emotion indicator. Obviously, not all the messages in corpus contain emojis. Thus, it was decided to build 5 classifiers, one for each emotions, one for each emotion, trained on those objectively labeled messages. Those classifiers then label the rest of the data. So how exactly was it done? Firstly, the images that were used less than 40 times overall were removed from the observed data. The rest of the images were grouped into 4 sets according to the expressed emotion, which was identified by manually analyzing the context. You can see it on the screen. And also it needs to be mentioned that neutral messages were annotated manually because they do not explicitly express any emotions and include images quite rarely.
Okay, in the next step, all messages containing non-standard, irony, or sarcasm use of emoji were excluded. The number of messages with emoji used in the direct meaning was 4,500 out of 11,287 messages containing emoji. Whether the use of emoji was direct or non-standard was estimated manually as well. The messages from the final dataset were divided into training set and validation set, containing 2,300 and 2,200 messages respectively. Then, in order to obtain 5 binary classifiers, either logistic regression or multinomial naive Bayes was used. For this purpose, we labeled the expected class as 1 and other emotions as 0. This is 1 versus all strategy. The classifiers had an F1 score of 90 to 93%. Finally, after the classifiers predicted emotions for the rest of the text messages, only those messages were selected, which were chosen by only 1 classifier. The resulting dataset of labeled messages contains 19,000 to 24,000 examples of each emotion and 110,000 items in total. So let's talk about model development. In order to extract features from the label data, the sklearn idea vectorizer was used, yielding 29,714 features. After training some traditional machine learning models, the following results were obtained. You can see them on the slide. It should be noted that we used a validation set and the metrics used were normalized for class imbalance. For further work, we chose the logistic regression as it proved to be the best fit for the data and the features we used. So, to combat overfitting, the logistic regression function was regularized. As a result, classifier performance reached 1.718, so it's F1 score.
Okay, so let's discuss results and let's start with human performance. So to assess the model against human performance, an experiment was conducted. 4 people aged 18-19 years were asked to label a data set containing 250 random messages from the validation set. As a result, it was found that human annotators perform only slightly better than our model. Their F1 score was 0.74 on average. In addition, agreement between different annotators was 70%. A similar result was obtained by another group of researchers. Thus, we can assume that the proposed classifier has near human performance. So, what about feature importance? However, as it was expected, the classifier performance was different for different emotions. Percentage of correctly labeled emotions ranged from 0.5 to 0.8. And the happiness class presented the least challenge, as you can see on the slide, and sadness and neutrality were both quite difficult for our classifier to classify. And in order to get insights into the reasons for such a difference, feature importance analysis was conducted. Next. The most important features were chosen using an algorithm based on HE2 applied to the TF-IDF feature matrix. Back, Sasha. Too soon. A few observations can be made here. Sasha, could you please get the... No, previous one. This one. Yeah, thanks so much. Yeah. Previous one, Sasha. A few observations, yes, a few observations can be made here. Firstly, there is a drastic difference in terms of overall register, as you can see. Neutrality and uncertainty tend to contain more sophisticated vocabulary than any other class. Anger, on the other hand, possesses a lot of explicit language. Also, other observations include the fact that negative pronouns are mainly found in sadness, while interrogative and indefinite ones in uncertainty, and so on. But despite these characteristics, it is evident that these clusters of selected features are not exactly equal concerning exhaustiveness. For example, the list of lexical markers for happiness appears to be more descriptive of the target class than that of neutrality. And this naturally results in neutrality being less recognizable by our model than happiness. And in order to provide comprehensive evaluation of each of the groups of features, it was decided to manually analyze the morphological composition and estimate the proportion of denotative, facultative, and potential amatives. Moreover, the scale of expressiveness was also added. Yeah. So it is quite obvious from this graph that such features as denotative amatives, adjectives, and expressiveness are crucial for emotion recognition, as they are highly correlated with the emotion itself. Sasha, your mic is off. Sasha.
It's crucial to analyze the mistakes our model is prone to. As you can see from the presented graph, top three error types are sadness, being confused with other non-positive emotions. Regarding sadness and anger confusion, mistakes of this type occur due to overlapping lists of features. Both sadness and anger messages tend to contain such markers as explicit language, which makes it harder to distinguish between them. As for the lack of distinction between sadness and neutrality, error analysis has shown that it's due to the total absence of denotative amatives in the neutrality class. If you remember, the list of features of neutrality class consists almost entirely of potential amatives. Consequently, whenever a neutral message contains a stronger amative of sadness, it's misclassified as such. Speaking of the reason for which sadness and uncertainty tend to be confused, one interpretation is that such emotions are often present in a message simultaneously, since it's natural for a person to be upset and afraid and surprised at the same time. Okay. Taking it all into consideration, it's expected that the following steps will help eliminate errors and enhance the model's performance. So, we plan to correct the model's behavior concerning explicit language, exclude random word features from neutrality, and manually find and add more distinctive markers, not only words, but probably other linguistic levels as well. Manually add a greater number of denotative amatives to the list of features, use a different emotion classification and or to account for multiple emotions expressed in one message. So, for the purpose of finding more features, it was decided to test the new markers obtained during feature and error analysis using tree-based ensemble models. The following markers were selected as most significant. These are number of nouns, number of word spasibo or thanks, ratio of function words, message length in words, verb ratio, maximal length of a word in the message, presence of function words, the number of interrogative pronouns, and message length in symbols. Apart from this, it's also necessary to work out a way of distinguishing the register of words in a message, as it might improve the model's performance by enhancing the recognizability of neutrality and uncertainty classes.
So yeah, this is how we address the problem of developing an integrated approach to emotion classification combining both linguistic analysis and machine learning. We presented a new semi-automatically generated data set that was based on processing 1,800,000 messages. And we also proposed an automatic classifier of emotions presented in informal text messages in Russian with F1 score of 0.718, which is found to be close to human level performance. And Sasha, will you talk about future work?
Feature importance analysis has shown that denotative emotives, yeah, future work includes changing its behavior concerning insignificant features and adding important ones. Moreover, we plan to extend the emotion classification by adding the emotions of contempt and disgust and differentiating between fear and surprise classes. Finally, we plan to implement multi-level classification, as there are cases when the same short text or even a single sentence contains more than one emotion. So that's all, I guess.
Thank you for your attention.
Okay, there is a question in a group chat for you. What's about BERT? Did you try it? Can you say something about it?
Sasha, can you?
No, we haven't tried BERT. Yeah, we haven't tried BERT because, okay, we tried only machine learning models at this stage because we have not really much data, and using deep learning models, including BERT, and using different embeddings we just plan to do that in the future and not at this stage. Now we have these results, I can say, as a baseline, because this is the first solution of this problem for the Russian language, as I know. So yeah, it will be in the future and not now.
Okay, thank you. The second question is, does it make sense to classify firstly by sentence, positive, negative, neutral, and then by those emotions? It seems that any emotion can be attributes to one of those types. Have you tried it, or are you planning to do it? What do you think about it?
In fact, we are planning to do this, to construct this sort of pipeline thing where
we
classifiers.
We had some plans to. Okay.
Who will speak? Yeah, we are planning on making such a pipeline thing where there will be a lot of binary classificators constructed one by one. And well, there is in fact a problem that such emotions as surprise, for example, are a little bit hard to classify whether it's a good sentiment or not. So yeah, it has some questions, but we are actually solving it right now. So yeah.
Okay, the one question that I had is, are you planning to publish the data set?
Yeah, we published this data set.
With text, right?
Yeah, with text.
And how much data?
We published it on GitHub, on our GitHub repository.
How much data did you crawl from Vkontakte? I mean, you can't publish Vkontakte texts if I remember guidelines correctly. I mean, you can crawl from Vkontakte and publish it.
Okay.
So it's illegal. Maybe you should think about it. Yeah, and it's just my suggestion to think about it and read properly.
We parsed in Telegram, not just publish them, and yeah, and so that we anonymized half of the data. Yeah, we manually anonymized half of the data from Contact and Telegram. We removed all phone numbers, all surnames, all places, and so on. So it can be really anonymous. And we published half of the data set containing nearly 50,000 messages from these two social networks. So yeah, they were manually anonymized and published on our GitHub repository, and our paper has links to it.
Okay, thank you. And one more questions from Andrei Kutuzov. Andrei, go ahead and just ask.
Yep. So I have a small question about the publication history of this paper. So as far as I can tell, you have already published a paper with the same name at Dialogue this year. So what has changed? I mean, what additional research have you done since then? Because it really seems that the Dialogue paper by the same authors and the IAST paper are really similar.
Well, there is a certain novelty to this version of article, and it is a bit more thorough interpretation, a bit of a more thorough error analysis and feature importance, and we also included information about searching for more features. Concerning our paper at the Dialogue conference, there are almost, no interpretation going on. There are most of those technical things like rates and coefficients, but here we are trying to get to the bottom of things and to explain why something works and why something doesn't work and what we can actually do about it. And in this version of paper, we also included information about some new experimental things. They are not crucial or way too significant to be, game-changing, but still they add a little bit to the actual results. So yeah, I would say that this is the same research, of course, but here we have just a longer extended version, which takes into account more things. Yeah.
Okay, thanks. But still, I think.
Okay, I can add that.
So consider
I think
changing.
my contribution
the
comparing to the Dialogue paper.
Okay, so let's continue with this next question from Natalia Lukashevich.
Если можно по-русски, слышно меня?
Слышно.
Да, я решила все-таки сделать замечание, скорее по форме представления. Мне кажется, тяжеловато для слушателя, когда вы меняетесь каждый слайд и выкрикиваете друг друга. Мне кажется, что все-таки смыслу это не помогает, поэтому по возможности, может быть, будете что-то еще рассказывать, делитесь, если вы хотите поделить между собой, то поделите все-таки больше части, потому что действительно взаимодействие сейчас очень сложное, но вообще всегда сложно, даже если вы стояли рядом в аудитории, представляете, вы бегали бы, то есть все это не очень хорошо, и просто, да, нам тяжело, нам слушателям было тяжело между, так сказать, слушателем в таком режиме, поэтому я решила сказать. Вот так. Все, спасибо.
Okay, thanks.
Thank you.
Yes, let's thank the speaker virtually. I can actually do. So the next